Have you ever looked up at the night sky and felt a strange, almost imperceptible sense that something is moving out there in the vast darkness, something immense and unseen, pulling at the very fabric of reality? Most of us grow up learning that the universe is expanding uniformly, with galaxies drifting apart in a calm, predictable dance. But what if I told you that astronomers have discovered something that shatters that peaceful image? Something that suggests entire clusters of galaxies are streaming in one particular direction, as if drawn by a force beyond our comprehension. This isn't science fiction, it's one of the most bewildering mysteries in modern astronomy, a phenomenon known as dark flow. Dark flow challenges everything we thought we knew about the cosmos. Imagine pouring water into a bowl and watching it not spread evenly, but instead rush toward one edge, defying gravity and logic. That's the level of strangeness we're dealing with here. For decades, scientists believed the universe was isotropic, meaning it looks the same in every direction. But dark flow hints at a cosmic preference, a mysterious current flowing through space on a scale so vast it's almost impossible to wrap your mind around. We're talking about thousands of galaxies moving together, tugged by something or somewhere we can't see. This journey we're about to take isn't just about facts and figures. It's about peering into the unknown corners of existence where the rules we've always trusted might not apply. Dark flow raises profound questions. Is there something beyond the observable universe influencing everything we see? Are we part of a larger structure we can't yet perceive? In this video, we'll explore 30 astonishing facts about dark flow, each one peeling back a layer of this cosmic enigma. You'll come away not just with knowledge, but with a sense of awe at how much remains to be discovered. So settle in, open your mind, and let's venture into one of the greatest puzzles the universe has ever presented to us. The story of dark flow's discovery begins not with a telescope pointed at stars, but with a satellite meticulously mapping the faint afterglow of creation itself, the cosmic microwave background. This remnant radiation from the Big Bang fills the entire sky, a nearly uniform blanket of microwaves that serves as the most fundamental proof of our universe's explosive origin. For years, this map was considered the ultimate reference frame, the still backdrop against which all cosmic motion could be measured. It was against this canvas that a team of astronomers, led by Alexander Kashlinsky, made an observation so strange it seemed to defy the canvas itself. Using data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, the team wasn't initially looking for anomalies. Their work involved studying the motion of enormous galaxy clusters, some of the largest structures in the universe. They knew these clusters should exhibit a subtle, predictable motion due to the gravitational tug of war between them, a phenomenon known as the kinetic Sunyaev-Zeldovich effect. This effect creates a tiny distortion in the cosmic microwave background as the hot gas within a moving cluster scatters the ancient photons. By carefully mapping these distortions for over 700 clusters, the team could essentially chart their velocities. What they found, published in 2008, was not subtle. It was a shock. Instead of a random, meandering drift, the data revealed a staggering, coordinated flow. These colossal clusters, some containing thousands of galaxies, were all streaming at breathtaking speeds, over 2 million miles per hour toward a single patch of space between the constellations of Centaurus and Vela. This wasn't a local effect. It was detected in clusters billions of light-years apart, meaning this coherent motion was happening on a scale that encompasses a significant portion of our observable universe. The most baffling part was that this motion was in addition to the universe's overall expansion. It was a directed current within the expanding ocean of space, a current with no obvious source. According to the standard model of cosmology, the universe is homogeneous and isotropic on large scales. The gravitational influences of all the matter we can see and the dark matter we infer should cancel out over such vast distances. There simply shouldn't be a preferred direction on a cosmic scale. The sheer scale and coordination of this motion pointed to a gravitational source of unimaginable power, but one that lay outside our observable horizon. Kashlinsky's team had inadvertently found evidence that our entire cosmic neighborhood, perhaps even the universe itself, is not the isolated island we thought it was, but is instead being pulled by something beyond the edge of everything we can see. So what exactly is this mysterious current they discovered? Let's break it down. Dark flow is the name given to the observed, coordinated movement of entire galaxy clusters. We're not talking about a gentle drift or a slow meander. These are the largest known structures in the universe, some containing thousands of individual galaxies, all moving together at astonishing speeds, up to 1,000 kilometers per second. To put that into perspective, that's over 2 million miles per hour. At that rate, you could travel from Earth to the Moon in under 4 minutes. This isn't random motion. It's a coherent flow, like a mighty river of galaxies all streaming toward a single, specific destination in the cosmos. The most critical part of this definition, and the reason it's so baffling to scientists, is the source of this motion. According to our fundamental understanding of gravity, the only thing that can make something this massive move this quickly is an even more immense gravitational pull. We can map the distribution of all the matter we can see: stars, galaxies, nebulae, and all the dark matter we infer from its gravitational effects. But when we add it all up, the combined gravitational attraction of everything in our observable universe simply isn't strong enough and isn't organized in the right way to explain this kind of large-scale, coordinated motion. The gravitational tug from all known sources should have cancelled itself out over such vast distances. The force pulling these clusters is so powerful that its source must lie beyond the horizon of everything we can possibly observe with our most powerful telescopes. This leads to a truly staggering implication. Dark flow suggests that the structure of the cosmos extends far beyond what we call the observable universe. Our entire cosmic neighborhood, everything we can see and measure, might be just a small part of a much larger, grander structure, and something immense, perhaps another universe, a region of space with wildly different physical properties, or a concentration of mass and energy on a scale we can't even conceive is out there, exerting its gravitational influence on us. It means the universe might not be isotropic or the same in all directions after all. There might be a genuine preferred direction in the cosmos, and we are all, on some imperceptible level, flowing with its current. Now, to truly grasp the scale of this mystery, we need to talk about the sheer, impossible speed involved. We've all heard that space is expanding, with galaxies receding from us in a way that's often described as a calm, steady drift. This is Hubble's law in action, the cornerstone of modern cosmology. But dark flow isn't that. This is something else entirely, a directed, high-velocity current superimposed on top of that gentle expansion. The galaxy clusters caught in this flow are moving at a consistent velocity of around 1,000 kilometers per second. That number might feel abstract, so let's give it some context. A bullet from a high-powered rifle travels at roughly 1 kilometer per second. The International Space Station orbits Earth at about 7.7 kilometers per second. Even our entire solar system, as it orbits the center of our Milky Way galaxy, does so at a respectable 230 kilometers per second. The speed of dark flow makes all of that seem like a leisurely stroll. It is over 1,000 times faster than a speeding bullet and more than 4 times faster than our sun's journey around the galaxy. This velocity becomes truly mind-bending when you consider the distances. These aren't single stars or small galaxies moving. These are colossal clusters, some spanning tens of millions of light years. To set all that immense mass into such a rapid, synchronized motion requires a gravitational pull of almost inconceivable power, and this is where our standard models of the universe hit a wall. According to everything we understand, the mass required to generate that kind of gravitational force on such a scale should be visible to us. Its gravitational influence should be woven into the very fabric of the cosmos we can observe. But it's not there. The map of known matter and dark matter in our observable universe shows no such concentration of mass in the direction of the flow. It's like being in a boat on a calm lake and suddenly feeling a powerful current pulling you, yet seeing no river inlet, no waterfall, nothing on the horizon that could possibly be the source. The current is undeniable, but its origin is completely invisible. This defiance of Hubble's law is what makes dark flow so revolutionary. Hubble's law describes a universe where everything is smoothly moving apart, with velocity increasing with distance in a very predictable way. Dark flow is a different kind of motion altogether. It's a bulk flow where huge swaths of space are moving in a specific direction as a single unit. It suggests that the fabric of space-time itself might be sliding toward some unseen attractor. For this to happen on a scale that encompasses billions of light years, the source of the pull must be so far away that its light hasn't had time to reach us yet in the entire 13.8 billion year history of the universe. We are quite literally feeling the gravitational tide of something that lies beyond our cosmic horizon, a region of space whose existence we can only infer from its profound and unsettling pull on everything we can see. This coordinated movement is not aimless. The data points to a specific and deeply mysterious destination in the sky. All of this flow, thousands of galaxy clusters moving at impossible speeds, is directed toward a single patch of space located between the constellations of Centaurus and Vela. For astronomers, naming this target was almost instinctive. They called it the dark flow dipole, but its pull felt so immense that it evoked the name of another legendary cosmic mystery from years past, the Great Attractor. Yet, this new attractor is something far stranger and more powerful. The original Great Attractor, discovered decades ago, is a gravitational anomaly located about 250 million light-years away in the direction of the Centaurus constellation. It's pulling our own Milky Way and thousands of other galaxies toward it. We believe it to be a massive concentration of matter, likely a huge supercluster of galaxies, and while it's shrouded by the dust of our own galaxy's central plane, making it difficult to observe directly, it still fits within our understanding of the universe's large-scale structure. It's a part of our observable cosmic neighborhood. The destination of dark flow, however, is a different beast entirely. It's not merely hidden behind a veil of dust, it appears to exist beyond the veil of everything we can see. The most crucial piece of evidence for this is the sheer distance of the galaxy clusters exhibiting this motion. Remember, astronomers measured this flow in clusters that are billions of light years away from us. The original Great Attractor's influence simply cannot extend that far. Its gravitational pull would be far too weak to create such a coherent, high-speed flow over such unimaginable distances. This means the source of dark flow's pull must be much, much farther away, lying far past the original Great Attractor, in a region of space whose light has not had enough time since the Big Bang to ever reach our telescopes. This is the heart of the directional mystery. We are being pulled toward a point in our sky, but the true source of that pull is invisible because it exists outside our observable universe. It's as if we're on a ship feeling a powerful current, and we can point exactly toward the horizon where it's coming from, but a perpetual, impenetrable fog prevents us from ever seeing what lies there. This realization forces us to confront a profound and humbling question. What is the nature of the cosmos beyond the cosmic horizon? The standard model of cosmology assumes a uniform universe that extends far beyond what we can see, but dark flow suggests that this unseen region might not be uniform at all. It might contain structures of such colossal size and mass that they defy our current laws of physics. perhaps remnants from the very earliest moments of the Big Bang or evidence of other universes exerting a gravitational influence from their own separate domains within a vast multiverse. The direction is clear, but the destination remains one of the greatest enigmas science has ever faced. Now, this discovery of a preferred direction in the cosmos strikes at the very heart of a foundational idea in astronomy, one that has guided our understanding for over a century, the cosmological principle. This principle is not just a minor theory, it's the bedrock upon which almost all of modern cosmology is built. In its simplest terms, it states that the universe is both homogeneous and isotropic. Homogeneous means that matter is distributed evenly when you look at the universe on a sufficiently large scale. There are no special spots. No matter where you are, the view should be roughly the same. Isotropic means it looks the same in every direction you point your telescope. There are no cosmic landmarks that make one direction inherently different from another. This assumption of a smooth, featureless universe is what allowed scientists to apply the laws of physics uniformly and develop our standard model of the Big Bang. Dark flow throws a monumental wrench into this elegant, orderly view. The coordinated motion of galaxy clusters toward a single point in the sky is the very definition of a preferred direction. It suggests that on the largest scales we can measure, the universe is not the same in all directions. There is a distinct this way and that way, a cosmic current that hints at a fundamental lopsidedness to existence. Imagine you're in the middle of a vast, supposedly featureless ocean. According to all your charts, the water should be still and uniform for miles in every direction. But then you feel a powerful, undeniable current pulling you steadily east. Your charts are suddenly wrong. The ocean isn't featureless, it has a flow, a structure you weren't aware of. That's the profound challenge dark flow presents to the cosmological principle. This forces a truly radical reconsideration of our fundamental assumptions. For decades, the principle has been so widely accepted that it's treated almost as a fact of nature. Our maps of the cosmic microwave background, aside from tiny fluctuations, largely support this idea of a uniform universe. But if dark flow is confirmed and its implications are fully accepted, we must ask, is the principle only true for the observable universe, our limited bubble of space? Does the principle break down beyond our horizon, in regions we can never see? The gravitational pull causing dark flow must be coming from something so massive and so distant that it lies in this unobservable territory. This means our entire cosmic neighborhood, everything we can study, might not be a representative sample of the whole universe. We could be living in a Chinese letter, a province of a much larger and far more structured cosmos, one that doesn't play by the simple, uniform rules we've written for it. To fully appreciate why dark flow is so unnerving to scientists, we need to understand what it is not. The cosmos is filled with motion, much of which we can explain with elegant equations and well-understood physics. For instance, every galaxy has what's called a peculiar velocity. This is a slight deviation from the smooth, uniform expansion of the universe described by Hubble's law. Our own Milky Way, for example, has a peculiar velocity as it's gently tugged by the gravitational influence of our nearby galactic neighbors, like Andromeda, and larger structures like the Virgo cluster. These are local motions caused by the gravitational dance of objects that are relatively close to each other in the cosmic scheme of things. They are the celestial equivalent of eddies and small currents in a vast ocean, predictable and contained. Then there are larger, coordinated movements known as bulk flows. These occur when a large group of galaxies moves together in a somewhat coherent way, pulled by a massive, nearby gravitational source. The most famous example is the original great attractor we mentioned earlier. It's pulling our local group of galaxies and thousands of others in its direction. But critically, these bulk flows are regional phenomena. their influence is limited to a certain volume of space, perhaps a few 100 million light-years across. Once you map the distribution of visible and dark matter in that region, the source of the gravitational pull becomes clear. It's a puzzle, but one where all the pieces are present on the table. Dark flow is fundamentally different. It is not a local eddy or a regional current. The key distinction lies in the staggering scale and coordination of the movement. The galaxy clusters exhibiting this flow are not neighbors. They are separated by billions of light years. For these immensely distant and isolated structures to all share the same high-velocity motion toward the same point in the sky, the gravitational source cannot be local or even regional. The known gravitational influences from all the matter in our observable universe simply do not have the reach or the power to orchestrate such a synchronized motion across such mind-boggling distances. It would be like people in different countries all simultaneously starting to walk westward. You could explain it if there was a giant magnet in the ocean pulling everyone, but if your map shows no such magnet, the phenomenon becomes inexplicable. This is why dark flow isn't just another bulk flow. It's a universal flow, a current that seems to be woven into the fabric of spacetime itself on the grandest possible scale, hinting at a source of influence from a realm we cannot see or directly measure. Dark matter has been the unsung hero of cosmology for decades, the invisible hand that sculpts the universe. We can't see it, but we see its work everywhere. It's the glue that holds spinning galaxies together, preventing them from flying apart, and it's the hidden scaffolding upon which the vast cosmic web of galaxies is built. Its gravitational influence perfectly explains the rotational speeds of galaxies and the motion of galaxies within clusters. For so long, it seemed like the final piece of the puzzle, the missing ingredient that made our models of the universe finally click into place. But dark flow presents a challenge that even dark matter in its current form cannot overcome. The fundamental issue is one of scale and distribution. The dark matter we infer from its gravitational effects isn't a single, monolithic entity. It's woven throughout the entire observable universe, forming a massive, intricate network often called the cosmic web. This web has dense nodes, the halos surrounding galaxy clusters, and vast, empty filaments stretching between them. Crucially, according to our best simulations, this distribution is still fundamentally homogeneous and isotropic when averaged over extremely large scales. The gravitational pulls from all these different clumps and filaments of dark matter should, in theory, cancel each other out over the mind-boggling distances separating the galaxy clusters caught in dark flow. There should be no net gravitational force strong enough or coherent enough to make clusters billions of light years apart all stream in the same direction at the same incredible speed. It would be like millions of different people all around the world gently tugging on a single rope in different directions. The rope might twitch, but it wouldn't launch in one specific direction with immense force. Think of it this way: the dark matter we know and rely on is like the atmosphere. It's everywhere. It has local currents and weather patterns, but it doesn't create a global wind that blows everything on the entire planet in one single direction. Dark flow requires that global wind. It requires a gravitational gradient on a scale larger than the entire observable universe, a slope in the fabric of spacetime so vast and steep that everything on our side of the horizon is sliding down it. The known inventory of dark matter, as vast as it is entirely contained within our observable horizon. Therefore, its gravitational influence cannot create a preferential pull from one specific direction beyond that horizon. For dark flow to be real, its cause must be something even more extraordinary than dark matter, a gravitational source from a realm beyond our own, a place where the rules of our observable cosmos may not even apply. So how do you even begin to measure something as elusive as a current flowing through the cosmos? The answer lies in a brilliant and delicate technique that uses the oldest light in the universe as a stationary backdrop. To detect the motion of these immense galaxy clusters, astronomers turn to the cosmic microwave background, that ancient afterglow from the Big Bang that permeates all of space. This radiation is our universal reference frame because it fills the entire universe evenly. Any tiny, specific distortions in it can be used as a measuring stick for motion. The specific distortion they were looking for is known as the kinematic Sunyaev-Zeldovich effect. That's a mouthful, but the concept behind it is utterly fascinating. Let's break it down step by step. Imagine the cosmic microwave background as a uniform, faint glow of microwave light coming at us from every direction in the sky. Now picture a massive cluster of galaxies moving through space. This cluster isn't empty, it's filled with incredibly hot gas, a plasma of charged particles. As this cluster moves, it plows through this sea of ancient CMB photons. When a photon from the CMB radiation collides with a fast-moving electron in that hot cluster gas, something crucial happens. The photon gets a boost of energy, a process inverse to the more familiar Compton scattering. Here's the critical part. The direction of the cluster's motion changes the nature of this energy transfer. If the cluster is moving toward us, the photons that scatter off its electrons get an extra kick, shifting them to a slightly higher energy frequency. Conversely, if the cluster is moving away from us, the photons lose a bit of energy and shift to a slightly lower frequency. This interaction creates a minuscule but measurable distortion in the CMB's temperature, precisely in the direction of that galaxy cluster. In the part of the sky covered by the cluster, the uniform microwave background will appear ever so slightly hotter or colder than the surrounding areas. This temperature shift is the telltale signature of the kinematic Sunyaev-Zeldovich effect, and it directly encodes the cluster's velocity through space. Detecting this effect is a monumental feat of precision. The temperature changes involved are incredibly subtle, on the order of millionths of a degree. It requires exceptionally sensitive instruments, like those on the Wilkinson microwave anisotropy probe and later the Planck satellite, which were designed to map the CMB in exquisite detail. The process isn't about looking at one cluster either. To have any confidence in a measurement as grand as dark flow, scientists had to meticulously analyze this effect for hundreds of clusters spread across the sky and at vastly different distances from us. They weren't just looking for random motion, they were searching for a pattern. When the data from all these disparate clusters was compiled, the pattern that emerged was unmistakable and shocking. A statistically significant number of them showed a velocity component pointing toward the same distant patch of sky. This wasn't a measurement of one object moving. It was a measurement of the fabric of space-time itself in motion. Read through the faintest of imprints on the oldest light we can see. Of course, any finding that challenges the very foundations of cosmology is bound to face intense scrutiny, and dark flow was no exception. The initial announcement sent ripples through the astrophysics community, sparking a fierce and ongoing debate that pits extraordinary evidence against extraordinary claims. On one side are the discoverers, convinced they have found a crack in our standard model of the universe. On the other are skeptics who argue that the signal is not a cosmic current, but a subtle artifact hidden within the immense complexity of the data itself. A primary point of contention lies in the statistical significance of the findings. Skeptics argue that the measured velocities derived from the incredibly faint kinematic Sunyaev-Zeldovich effect are pushing up against the very limits of what our instruments can detect. They point out that the measured temperature distortions are minuscule, and that the process of extracting a velocity signal requires meticulously subtracting a myriad of other foreground signals, everything from dust in our own galaxy to the emission from other distant galaxies. The concern is that what looks like a coherent flow could, in fact, be the accumulated result of many tiny, uncorrected errors in this subtraction process. If even a small systematic bias exists in the data processing pipeline, it could artificially create the appearance of a bulk motion where none truly exists. It's like trying to hear a whisper in a crowded, noisy room. You might be convinced you heard something, but it's incredibly difficult to be sure it wasn't just the rustle of a jacket or the hum of the air conditioner. In response to these concerns, other teams have attempted to replicate the findings using different methodologies and data from newer satellites, most notably the European Space Agency's Planck mission, which provided an even more precise map of the cosmic microwave background. Some of these subsequent analyses failed to detect the dark flow signal with the same strength or confidence, fueling the skepticism. These teams suggested that more careful handling of the data, accounting for additional subtle effects like the gravitational lensing of the CMB itself, could wash out the apparent flow. They proposed that once all known variables are perfectly accounted for, the unusual motion might simply vanish, leaving behind the calm, uniform expansion we expect. Yet, the story is far from one-sided. Alexander Kashlinsky and his team have vigorously defended their work, conducting further studies with larger samples of clusters and more refined analysis techniques. They maintain that the signal not only persists but grows stronger with more data. They argue that their methods for cleaning the data of foreground contaminants are robust and that the statistical significance of the flow remains high. This back and forth is not a sign of failure in science. It is science working as it should. It's a rigorous process of claim, counterclaim, verification, and refinement. The very existence of this heated discourse underscores the monumental implications of dark flow. Nobody is debating minor details. They are arguing over whether we need to rewrite the basic rules of our cosmic address. This ongoing dialogue, conducted in academic papers and at conferences, is the essential crucible through which a truly revolutionary idea must pass to earn its place in our understanding of the universe. Into this heated scientific debate entered a new player with the potential to settle the argument: the European Space Agency's Planck satellite. Launched in 2009, Planck was a technological marvel designed to map the cosmic microwave background with unprecedented sensitivity and resolution. Its instruments were significantly more advanced than those on WMAP, allowing it to measure the faint temperature fluctuations of the ancient radiation with a precision that was little short of miraculous. If the dark flow signal was a real cosmic phenomenon, Planck would be the instrument to either confirm it beyond a shadow of a doubt or reveal it as a tantalizing but ultimately false reading. The scientific community waited with bated breath for the Planck team's analysis. When the results were published, they did not provide a simple, clear-cut answer. Instead, they added fascinating new layers of complexity to the mystery. Planck's incredibly detailed data did indeed detect a bulk flow motion, a large-scale streaming of galaxy clusters. This in itself was a crucial finding. It confirmed that the anomalous motion first spotted in the WMAP data was not merely an instrumental glitch or a data processing error. There was a coherent motion happening on scales that challenged conventional models. However, the precise details of what Planck measured were slightly different from the original dark flow claims. The satellite's more sensitive instruments allowed scientists to filter out foreground noise, like the faint glow of dust in our own galaxy, with far greater accuracy. What remained was a subtler but still statistically significant signal. Some analyses of the Planck data suggested the flow might extend to slightly shallower distances than initially proposed, while others continued to support a more profound reach. The key takeaway wasn't that Planck debunked dark flow, but that it refined it. The satellite's superior data confirmed the existence of a mysterious, large-scale bulk flow, but its exact scale and amplitude became a new point for discussion. This is a common pattern in cutting-edge science. Better technology doesn't always immediately solve a mystery. Instead, it often provides a sharper, more detailed view of the mystery itself, revealing nuances we never knew were there. Think of it like improving a telescope. At first, you see a blurry smudge of light in the sky. With a better telescope, that smudge resolves into a distinct galaxy. With an even more powerful instrument, you can then see intricate spiral arms and dust lanes within that galaxy. You haven't disproven the existence of the initial smudge, you've simply revealed its true, more complex nature. Planck acted as that more powerful instrument for dark flow. It moved the conversation from "is this real?" to "what exactly are we seeing?" Its confirmation of a large-scale anomalous flow legitimized the search for an explanation, forcing cosmologists to seriously grapple with the implications of a universe that might be fundamentally lopsided on the grandest of scales. To truly appreciate the staggering nature of dark flow, we must attempt to visualize distances so vast they defy human comprehension. We often hear the term billions of light years and nod, but its true meaning is almost impossible to grasp. A single light year is the distance light travels in 1 year, moving at over 186,000 miles per second. That's nearly 6 trillion miles. Now multiply that by several billion. The galaxy clusters exhibiting this mysterious flow aren't just a few million light years apart. They are separated by oceans of space measuring up to 3.5 billion light years across. This isn't merely a large structure, it constitutes a significant fraction of the entire observable universe, which itself is only about 93 billion light years in diameter. The flow encompasses a volume of space so immense that it could contain thousands of the largest known cosmic formations, like the Hercules Corona Borealis Great Wall, which is already a structure so colossal it challenges our understanding of how the universe evolved. This scale is what elevates dark flow from a curious anomaly to a potentially paradigm-shattering discovery. It is, without question, the largest and most coherent motion ever detected. When we talk about other bulk flows, like the one towards the original Great Attractor, we are discussing regional events on a scale of a few 100 million light years. Dark flow operates on a scale and order of magnitude larger. Imagine noticing that every single car on every highway across the entire continent of North America was not only moving but was also subtly drifting in the exact same direction, all at the same time. The local traffic patterns and individual destinations become irrelevant. A far more powerful, continent-wide force is at work. That is the level of coordination we are inferring from the data thousands of galaxy clusters, each a bustling metropolis of stars, all moving in concert across a continental scale of space. The sheer size of this phenomenon immediately rules out explanations that rely on the gravitational influence of any known or suspected structure within our observable cosmos. The gravitational pull from any object weakens with distance according to the inverse square law. For a source to exert a detectable force on a cluster 3 billion light years away, it would need to be of such unimaginable mass that its gravitational signature would be overwhelmingly obvious everywhere in the nearby universe. We would see its devastating effects on the cosmic web, warping the paths of galaxies and tearing apart the large-scale structure we observe, but our maps show no such monster. Therefore, the only logical conclusion is that the source of this titanic pull must lie beyond the veil of what we can see, in a realm whose physical properties remain a complete and utter mystery to us. We are sensing the wake of a giant that exists outside our universe's observable walls. This mysterious current flowing through the cosmos inevitably leads us back to the very beginning of everything, to a theory designed to explain the universe's large-scale uniformity, cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, the universe underwent an unimaginably rapid exponential expansion, smoothing it out and creating the conditions we see today. It's a cornerstone of modern cosmology, but dark flow presents it with a fascinating paradox. Inflation is meant to explain why the universe is so uniform, yet dark flow is a stunning example of potential non-uniformity, a preferred direction on the grandest scale. So, could this flow be a relic from that inflationary epoch, a ghostly imprint from the universe's first moments? One compelling possibility is that dark flow is a direct result of primordial gravitational waves or fluctuations that were imprinted on the fabric of spacetime during inflation itself. The theory allows for the existence of superhorizon perturbations, density variations on scales larger than our observable universe. These wouldn't be structures made of matter, but rather wrinkles in the very geometry of the cosmos, frozen into the expanding spacetime during inflation. If such a colossal wrinkle exists just beyond our horizon, a vast slope in the gravitational landscape, it could be gently tugging on everything within our observable bubble, creating the coherent motion we detect as dark flow. In this scenario, the flow isn't pointing toward a concentrated mass like a super-universe, but rather we are sliding down a hill that was carved into existence during the universe's first terrifyingly rapid expansion. However, this idea pushes the boundaries of inflation theory as we currently understand it. The standard inflationary model predicts that these primordial fluctuations should be random and without any preferred direction, leading to the isotropic universe described by the cosmological principle. For inflation to produce a gradient on a scale large enough to cause dark flow, it would require a significant tweak to the model. Perhaps the inflationary field had a slight anisotropy itself, or maybe the process of inflation ended differently in various directions, a concept known as anisotropic inflation. This isn't about discarding inflation, but rather about evolving it to accommodate a more complex and interesting cosmic birth. It suggests that the inflationary period might not have been perfectly smooth and uniform, but could have had its own textures and currents that are only now becoming detectable through their immense gravitational influence. This line of thinking opens the door to even more profound modifications. Some theoretical physicists propose that dark flow could be evidence of a pre-Big Bang geometry, a remnant of something that existed before our universe began. Imagine our entire cosmos in its infancy being born adjacent to another region of spacetime with vastly different properties. The gravitational pull from that other region, though now forever beyond our causal horizon, could have given our newborn universe a kind of kick, setting it into a bulk motion that has persisted for over 13 billion years. We would still be feeling that initial shove. This doesn't necessarily require a multiverse, but it fits comfortably within many multiverse theories, where our universe is one bubble among many in a grand cosmic foam, and the gravitational influence of a neighboring bubble is subtly tugging at our own. Whether it's a primordial hill or a ghostly hand from a neighboring realm, dark flow challenges us to consider that the story of our universe's origin may be far richer and more complex than we ever imagined. Perhaps the most thrilling and mind-bending explanation for dark flow is the possibility that we are feeling the gravitational tug of another universe entirely. This idea propels us straight into the realm of the multiverse hypothesis, a concept that has moved from the fringes of theoretical physics into a serious, though still highly speculative, area of cosmological debate. If dark flow is real and its source lies beyond our observable horizon, then one of the most elegant explanations is that something immense exists in that unobservable territory. But what could be more immense than another cosmos, with its own physical laws and concentrations of mass, exerting a pull on our own? Think of our observable universe not as the entirety of existence, but as a single bubble floating in a vast, frothy ocean of other bubbles, other universes. This is the foundational idea of the multiverse, often arising from theories like eternal inflation. In this model, the rapid expansion of spacetime never truly stops overall. Instead, it continues eternally, spawning an infinite number of pocket universes like ours, each with its own unique properties. Now, imagine two of these bubbles floating close to one another in this grand cosmic foam. Even though they are fundamentally separate realms, if they formed near each other, the spacetime between them could allow for a faint gravitational interaction. The immense mass of a neighboring universe could be pulling on the matter within our own, creating the coordinated stream we detect as dark flow. It would be a cosmic version of feeling the tide coming in from the ocean. You can't see the moon's gravitational pull, but you can see its undeniable effect on the water. This isn't just wild speculation. It's a hypothesis that some respected cosmologists have seriously proposed. The gravitational force, unlike the other fundamental forces, may be unique in its ability to leak between branes, a concept from string theory where our universe is a three-dimensional membrane floating in a higher dimensional space. If another universe brane exists parallel to ours in these higher dimensions, its gravity could theoretically influence us, providing a potential mechanism for the pull. Dark flow, in this context, becomes the first potential empirical evidence for something beyond our cosmic bubble, a shadow on the wall of our cave hinting at a reality vastly larger and more strange than we ever dreamed. Of course, this remains one of the most controversial ideas in modern science. The main criticism is that it ventures dangerously close to being an unfalsifiable claim. If the cause of the flow is forever hidden beyond our observational horizon, how can we ever truly prove it? Critics argue that invoking other universes to explain an anomaly can become a catch-all solution that halts further inquiry within our own cosmos. Yet, for its proponents, dark flow isn't just an easy answer. It's a tantalizing data point that aligns perfectly with pre-existing multiverse theories. It doesn't prove the multiverse, but it offers a specific, measurable phenomenon that the multiverse hypothesis could potentially explain. This transforms the discussion from pure mathematical abstraction into a tangible puzzle with observable consequences, pushing the boundaries of what we consider scientific inquiry and challenging us to find new ways to test the untestable. While the idea of a multiverse pull is undeniably captivating, the scientific process demands we first exhaust every possible explanation within the bounds of our known universe before venturing into the truly exotic. The extraordinary nature of the dark flow claim means it requires extraordinary evidence, and a significant part of the astrophysics community has dedicated itself to finding a more conventional culprit. These alternative explanations aren't about dismissing the mystery, but about rigorously testing it against every other possibility. A primary focus of skepticism lies in the immense challenge of the measurement itself. Detecting the kinematic Sunyaev-Zeldovich effect is an exercise in precision on an almost unimaginable scale. The temperature distortions scientists are looking for are minuscule, requiring them to filter out a cacophony of foreground noise. This includes everything from the faint glow of dust in our own Milky Way to the microwave emissions of distant galaxies. Critics argue that what appears to be a coherent flow could, in reality, be the accumulated result of many tiny, uncorrected errors in this incredibly complex data processing pipeline. If there's even a small, subtle bias in how this foreground subtraction is handled, a bias we don't yet understand, it could artificially create the signal of a bulk motion across the sky. It's like trying to measure the exact weight of a single feather on a scale that's also holding a bowling ball. You must be absolutely certain you've zeroed out the weight of the ball first, or your reading of the feather will be completely wrong. The concern is that we may not have perfectly zeroed out all the heavyweight foreground interference, leaving behind a phantom signal that looks like motion. Another compelling alternative suggests that we may have simply underestimated the gravitational power of structures within our own observable universe. Could there be an unknown, truly colossal supercluster of galaxies, a hypercluster of unimaginable size lurking in the zone of avoidance, the region of the sky obscured by the dense dust and stars of our own galaxy's central plane? This area is notoriously difficult to observe, and it's precisely in the direction toward which dark flow is pulling. Perhaps the original great attractor, itself once a mysterious anomaly, is merely the nearest tip of a far larger and more massive gravitational structure that extends much deeper into space. This greater attractor could theoretically exert a pull powerful enough to influence galaxies billions of light years away. However, this theory runs into a major problem with the standard model of cosmology, the speed at which such a structure would have to form. For gravity to assemble such an immense concentration of matter, it would have needed more time than the age of the universe allows. It would defy our understanding of structure formation, requiring a mechanism we haven't yet discovered. A third avenue of inquiry looks not at the clusters themselves, but at the backdrop against which they are measured, the cosmic microwave background. What if the anomaly isn't in the motion of the clusters, but in the CMB map we use as our stationary reference frame? The CMB is not perfectly uniform. It contains tiny fluctuations in temperature, often called anisotropies. Some researchers have proposed that a very large-scale, non-random pattern in these primordial fluctuations could create the illusion of a bulk flow. If the CMB itself has an intrinsic, large-scale gradient, meaning one hemisphere of the sky is very slightly hotter on average than the other, then the measurements of the kinematic Sunyaev-Zeldovich effect could be systematically misinterpreted. We would be measuring cluster motion against a backdrop that isn't as uniform as we assumed, like using a slightly warped ruler and getting incorrect measurements for everything you try to measure with it. This would mean the dark flow isn't a current in space, but a trick of the light, a profound illusion stemming from a peculiarity in the universe's oldest light. Each of these alternatives represents a diligent effort to solve the puzzle with the tools and understanding we already possess. They are not dismissals of the mystery, but essential steps in the scientific process, ensuring that we are not led astray by the seductive allure of a revolutionary discovery before we have definitively ruled out all more mundane possibilities. This rigorous debate is what ultimately strengthens our understanding, forcing us to refine our instruments, question our assumptions, and dig ever deeper into the data, whether the final answer lies within our cosmic horizon or far beyond it. To fully understand the profound nature of dark flow, it's essential to revisit another cosmic mystery that captivated astronomers decades ago, the Great Attractor. This enigmatic region of space, located around 250 million light-years away in the direction of the Centaurus constellation, has been pulling our Milky Way galaxy and thousands of others toward it with a powerful gravitational grip. For a long time, this was the most significant unexplained motion we knew of, a hidden focal point of immense mass obscured by the dusty central plane of our own galaxy, making it difficult to observe directly. We now believe the Great Attractor to be a colossal supercluster of galaxies, a dense knot in the cosmic web whose gravitational influence, while powerful, fits within our understanding of how structure forms in the universe. It is a regional anomaly, a massive but local concentration of matter that explains the motion of galaxies in our immediate cosmic neighborhood. Dark flow, however, is not merely an extension of the Great Attractor's influence. It is something categorically different and far more perplexing. While both phenomena involve large-scale gravitational pulls, the comparison ends there. The key distinction lies in the sheer reach of the force. The Great Attractor's gravitational power, as immense as it is, diminishes with distance according to the unbreakable inverse square law. Its influence is potent enough to orchestrate the motion of galaxies within a few 100 million light-years, but it is utterly incapable of affecting galaxy clusters that are billions of light-years away. The clusters exhibiting dark flow are so distant that the light we see from them left when the universe was less than half its current age. For the Great Attractor to pull on these ancient, far-flung structures, it would need to possess a gravitational strength that defies the known laws of physics. This difference in scale points to a fundamental difference in nature. The Great Attractor is a mystery of location. It's a what that is hidden behind the dust of our galaxy. Dark flow is a mystery of origin. It's a where that appears to be hidden beyond the very edge of the observable universe. One is a hidden monster within our cosmic house. The other is the scent of a monster from a house so distant we can never see it. The motion toward the great attractor is a local river current, powerful but understandable within the context of the surrounding watershed. Dark flow is the entire ocean tilting, suggesting the landscape of reality itself is sloping toward an unseen abyss. The direction of the flow is eerily similar, pointing toward the same general patch of sky, but this is likely a cosmic coincidence of alignment. It's as if we feel a local wind blowing from the east and then discover a hurricane-force gale also blowing from the east, but originating from a continent thousands of miles away that doesn't appear on any of our maps. This realization forces a dramatic upgrade in our cosmic vocabulary. We are no longer just searching for a great attractor, but for something infinitely more grand and mysterious. Some cosmologists have begun referring to the hypothetical source of dark flow as the beyond the great attractor or even the ultimate attractor. This terminology underscores the monumental leap in scale and mystery. The great attractor is a gravitational puzzle we expect to solve with better telescopes and surveys. The source of dark flow, if confirmed, is a gravitational paradox that challenges the very framework of our cosmology, suggesting that the forces shaping our universe operate on a canvas vastly larger than we ever imagined, a canvas that extends into realms we may never be able to directly observe. While dark flow presents a gravitational mystery pulling the cosmos in a specific direction, it exists alongside another, far more dominant force that does the exact opposite: dark energy. This enigmatic energy is believed to be responsible for the accelerating expansion of the universe, relentlessly pushing galaxies apart. At first glance, these two phenomena seem to be in direct opposition, one a vast, mysterious pull, the other a pervasive, repulsive push. This leads to a fascinating question. Could these two great cosmic unknowns be connected in some way, two sides of the same profound puzzle? On the surface, dark energy appears to be the antithesis of the force behind dark flow. Dark energy works uniformly across all of space, causing the very fabric of the universe to stretch at an ever-increasing rate. Its effect is isotropic, meaning it acts with equal strength in every direction, and it doesn't pull matter toward a point but rather creates more space between all points. This uniform outward push is the reason we see galaxies receding from us in a way that accelerates with distance. Dark flow, in stark contrast, is a highly directional phenomenon. It's a specific, coherent current within that expanding ocean, suggesting a gravitational attraction from one particular region of space. One force is a uniform push, the other is a directed pull. Because of this fundamental difference in their nature and action, most cosmologists treat them as separate, independent mysteries. The Standard Model holds that dark energy is a property of space itself, a cosmological constant, while the cause of dark flow, if real, is likely a gravitational anomaly from beyond our horizon. However, some theoretical physicists speculate that a connection isn't entirely out of the question. Could dark flow be influencing our measurements of dark energy, or vice versa? When astronomers measure the universe's expansion rate and acceleration, they rely on certain assumptions, primarily that the universe is homogeneous and isotropic. The existence of a large-scale bulk flow like dark flow directly challenges that assumption of isotropy. If our entire local universe is moving coherently, it could potentially introduce a slight bias into how we measure the expansion in different directions. Imagine trying to measure how quickly a river's current is speeding up while you yourself are in a boat being pulled by a separate, strong underwater current. Your measurements of the river's flow might be slightly skewed by your own motion. In a similar way, our peculiar motion due to dark flow could, in theory, need to be accounted for to get the most precise possible measurement of dark energy's effects. It's a subtle correction, but in the razor-sharp world of cosmology, every detail matters. But what about a deeper, more direct connection? Could dark energy itself be somehow responsible for dark flow? This possibility seems unlikely given our current understanding. The repulsive force of dark energy does not create gravitational gradients. It doesn't pull matter from one direction. Its action is perfectly even, like a rising tide that lifts all boats equally. It cannot explain why thousands of galaxy clusters would be streaming toward a specific point between Centaurus and Vela. For dark energy to cause a directional flow, it would have to be acting unevenly, something that would utterly shatter the cosmological principle in a way far more dramatic than dark flow itself. If dark energy were anisotropic, we would expect to see different rates of expansion in different parts of the sky, a phenomenon for which there is currently no strong evidence. Therefore, while dark energy defines the overall, accelerating expansion of the cosmic background, it leaves the mystery of the specific, superimposed current of dark flow entirely unanswered. Ultimately, the relationship between these two titans of modern cosmology is best described as a strange and beautiful cosmic dance between push and pull, expansion and attraction. Dark energy sets the stage. It is the dominant force governing the overall fate of the universe, dictating its accelerated expansion. Dark flow, meanwhile, is an intricate and mysterious step within that dance, a coordinated motion that plays out on top of the grand backdrop of expansion. One is the ocean itself, growing vaster by the moment. The other is a powerful current flowing within it. For now, they remain distinct enigmas, each challenging our understanding in its own unique way. Solving one will not necessarily solve the other, but unraveling the secrets of either will undoubtedly lead us to a richer, more complete, and likely far stranger picture of the cosmos we call home. The expanding universe is governed by one of its most critical numbers, the Hubble constant, which tells us precisely how fast space is stretching. But there's a problem, a significant and growing tension. When we measure this expansion rate using the early universe by studying the cosmic microwave background, we get one number. When we measure it using the late universe by observing the distances to nearby stars and supernova, we get a consistently higher number. These two methods, both rigorously tested, disagree. This isn't a small margin of error. It's a fundamental discrepancy that suggests a potential flaw in our standard model of cosmology, a model we've relied on for decades. It's as if two of the most precise clocks ever built are ticking at undeniably different rates, and no one can figure out why. This is where the mystery of dark flow enters the conversation in a fascinating way. Could this mysterious, large-scale current be subtly influencing our local measurements of the universe's expansion? The techniques used to measure the Hubble constant in the nearby universe, often called the distance ladder method, rely on establishing a chain of measurements that ultimately depends on our understanding of motion within our cosmic neighborhood. If our entire local group of galaxies and the larger supercluster we reside in is not just moving with the general expansion but is also caught in this additional, coherent dark flow stream, it could introduce a systematic error into our calculations. We might be misinterpreting some of the recession velocities we see, attributing them purely to the expansion of space when a component of it is actually this unexplained bulk motion. It's like trying to measure the speed of a river's current from a boat that itself is being pulled by a separate, strong underwater tow. Your measurement of the river's flow would be slightly off. Some cosmologists have proposed that properly accounting for the effects of a bulk flow like dark flow could help to reduce or perhaps even resolve the Hubble tension. The idea is that by meticulously subtracting the component of motion caused by this gravitational current from the observed velocities of nearby galaxies, we could get a cleaner, more accurate reading of the true expansion rate. It would be a crucial correction, potentially aligning the local measurements more closely with those predictions from the early universe. This would position dark flow not just as a bizarre anomaly, but as a vital key to solving one of the most pressing puzzles in modern cosmology, finally making the two most precise clocks in the universe tick in sync. However, this promising idea faces its own set of serious challenges. The magnitude of the Hubble tension is substantial, and the estimated velocity of dark flow, while immense, may not be large enough on our local scale to account for the entire discrepancy. Furthermore, the directionality of the flow is crucial. For it to significantly impact our local Hubble measurements, the flow would need to be aligned in a very specific way relative to our line of sight to the standard candles, the supernova and other objects we use to measure distance. A detailed analysis is required to see if the geometry of the effect fits. Initial studies suggest that while dark flow might contribute a piece of the puzzle, it is unlikely to be the sole solution to the Hubble tension. The mystery of the conflicting expansion rates likely has deeper, more fundamental roots, perhaps involving new physics related to dark energy or neutrinos. Ultimately, the potential connection between dark flow and the Hubble constant highlights a profound shift in how we view the cosmos. It forces us to accept that our position in the universe might not be as placid and unbiased as we once assumed. We can no longer take for granted that our local region is a perfectly still reference point from which to measure the universe's expansion. We must consider that we are in motion within a larger current, and that this motion could be obscuring our view of the fundamental laws governing all of reality. This doesn't simplify the Hubble tension. It adds a new layer of beautiful complexity, intertwining two of cosmology's greatest modern mysteries and suggesting that to understand one, we may first need to unravel the other. To solve a mystery on this scale, we need more than just better data. We need a revolution in how we observe the cosmos. The next generation of astronomical instruments, already in advanced planning stages, promises to be that revolution. These aren't mere incremental upgrades. They are telescopes and observatories designed to see farther with greater clarity and in more wavelengths than ever before, potentially giving us the tools to finally corner the dark flow enigma. One of the most anticipated tools is the Nancy Grace Roman Space Telescope, slated for launch later this decade. While its primary mission involves studying dark energy and exoplanets, Roman's powerful wide-field infrared instrument will conduct massive surveys of the sky. By peering through the obscuring dust of the Milky Way's plane with unprecedented clarity, it could finally reveal the full structure of the region toward which dark flow is pulling the zone of avoidance. If a previously unknown hypermassive cluster of galaxies is lurking there, a greater attractor, Roman is likely to find it, potentially providing a conventional explanation for at least part of the observed motion. Its ability to map the distribution of galaxies and dark matter in 3 dimensions will also provide an exquisitely detailed chart of the gravitational landscape of our local universe, allowing us to more accurately subtract all known influences to see what mysterious motion remains. Beyond Roman, astronomers are looking to a new technique that could provide an even cleaner measurement: the use of fast radio bursts, or FRB. These are incredibly brief, intensely powerful flashes of radio waves coming from deep space. While their origins are still debated, their usefulness as cosmic mile markers is undeniable. As an FRB signal travels across the universe, it interacts with the free electrons in galaxy clusters it passes through, creating a delay that is measurable. By analyzing a large number of FRBs from different directions and distances, scientists could potentially chart the large-scale motion of the intergalactic medium itself, independent of the cosmic microwave background. This would provide a completely independent test for dark flow, free from the potential systematics and foreground subtraction challenges that have plagued the CMB-based methods. If both the CMB and FRB techniques point to the same coherent flow, the evidence would become extraordinarily difficult to dismiss. Looking further into the future, concepts for even more ambitious observatories are on the drawing board. Imagine a successor to the Planck satellite, but with detectors so sensitive they could map the kinematic Sunyaev-Zeldovich effect not for hundreds, but for hundreds of thousands of galaxy clusters. Such a mission could create a dynamic velocity map of the entire observable universe, allowing us to see the flow in stunning detail and trace its evolution through cosmic time. Combined with data from the gravitational wave observatories of the future, which could sense the ripples in space-time from the very largest cosmic events, we might finally gather enough evidence to distinguish between a pull from a primordial super-horizon fluctuation and the gravitational tug of a neighboring universe in a vast multiverse. The path to solving dark flow is long, but the roadmap is clear, and the next generation of explorers is already building the vehicles for the journey. At the very heart of the dark flow controversy is a battle fought not with telescopes but with statistics. This isn't a simple disagreement over what was seen. It's a profound debate over how to interpret the faintest of whispers in an incredibly noisy dataset. Determining whether dark flow is a real cosmic phenomenon or a statistical phantom hinges entirely on its significance, a precise mathematical measure of how likely it is that the observed signal occurred purely by random chance. In science, a result is generally considered robust if the probability of it being a fluke is less than 5%, a threshold often called 5 sigma. The teams arguing over dark flow are grappling with results that sit in a much murkier, more contentious zone. The original team, led by Alexander Kashlinsky, employed a specific methodology to extract the velocity signal from the WMAP data. Their process involved meticulous and complex steps, identifying hundreds of galaxy clusters, carefully mapping the tiny temperature distortions in the cosmic microwave background caused by the kinematic Sunyaev-Zeldovich effect in the direction of each cluster, and then comparing these velocities to see if they showed a preferred direction. When they compiled the data, they argued the statistical significance was high, suggesting there was only a very small chance this coordinated motion was random. They saw a clear signal emerging from the cosmic static. However, other research groups soon began to poke holes in this statistical edifice. Their primary argument centers on the challenge of systematic errors, not mistakes but subtle, inherent biases that can creep into any complex measurement. The central question they raised is hauntingly simple. Are we certain we have perfectly removed every other possible source of that tiny temperature change? The list of potential contaminants is long and daunting. It includes the faint emission from dust within our own Milky Way galaxy, the microwave glow from distant, unresolved galaxies, and even subtle effects from the gravitational lensing of the CMB itself as its light warps around massive objects on its journey to us. Skeptics argue that if even one of these foreground signals is not modeled and subtracted with absolute perfection, its residual imprint could masquerade as the coherent motion of galaxy clusters. The fear is that the data processing pipeline itself might be inadvertently creating a pattern that looks like a flow. This led to a series of follow-up studies where different teams applied their own independent methods to analyze the same datasets. Some groups, using different statistical techniques or ways of modeling the foreground noise, found that the dark flow signal diminished dramatically, sometimes falling below the threshold of strong significance. For instance, analyzers of data from the Planck satellite, while confirming the existence of some large-scale bulk flow, often reported a lower amplitude and slightly different direction for it, suggesting the original detection might have been overstated. These teams contend that with more sophisticated data cleaning, the mysterious current seems to fade into the background, becoming consistent with the random fluctuations we might expect in a universe that is, on the largest scales, fundamentally uniform. In response, Kashlinsky and his colleagues have continually refined their own analysis. They've worked with larger catalogs of galaxy clusters and developed more robust methods for handling the foreground contaminants. With each iteration, they assert that the signal not only persists but becomes stronger and more statistically significant. They argue that their critics' methods are inadvertently subtracting out the very signal they're trying to detect, or that they are not using a large enough sample of distant clusters to see the effect clearly. This back and forth is a classic example of science in action, a rigorous, often fierce, dialogue where every assumption is challenged and every method is scrutinized. The difficulty in reaching a consensus underscores the extreme delicacy of the measurement. We are asking our instruments and our statistics to perform at the very absolute limit of their capabilities, teasing a whisper of a signal from a roaring symphony of cosmic noise. Until a new, completely independent method can verify the flow, this statistical stalemate is likely to remain the central battleground for the soul of this cosmic mystery. To fully grasp the sheer oddity of dark flow, it's helpful to place it side by side with other, more conventional types of cosmic motion we've observed for decades. Our universe is a dynamic place filled with movement at every scale, but not all flows are created equal. The most common motion is the gentle, predictable drift described by Hubble's law, the overall expansion of space itself, carrying galaxies apart like raisins in a rising loaf of bread. On top of this, we have the peculiar velocities of individual galaxies, small deviations caused by the gravitational tug of war with their immediate neighbors. Our own Milky Way, for instance, is gently pulled by the Andromeda Galaxy and the gravitational mass of the Virgo cluster. These are like small eddies and currents in a vast ocean, local and easily explained by the distribution of matter we can see and map. Then we have the larger phenomenon known as bulk flows. This is where a sizable group of galaxies, sometimes hundreds of millions of light years across, moves in a somewhat coordinated direction, pulled by a massive gravitational attractor. The most famous example is the motion toward the original great attractor. This is a genuine large-scale flow, but it is ultimately a regional event. We can identify the source. It's a concentration of mass, a supercluster of galaxies, hidden behind the dust of our own Milky Way. While it was a mystery initially, it fits within our understanding of cosmic structure formation. The gravitational pull is powerful but local, and its influence weakens predictably with distance according to the laws of physics. It's a current within the ocean, but we can see the river that feeds it. Dark flow is in an entirely different category. It shares a family resemblance with these bulk flows, but operates on a scale that renders them almost trivial by comparison. The key distinctions are threefold: scale, coherence, and inexplicability. First, the scale. The clusters caught in dark flow are not neighbors. They are separated by billions of light years. This flow encompasses a volume of space that represents a significant fraction of the entire observable universe. It is not a regional current, it is a potential continental drift of the cosmos itself. Second, the coherence. While other bulk flows show some degree of coordination, the motion detected in dark flow is stunningly uniform across these unimaginable distances. Galaxy clusters billions of light years apart are all moving at similar high speeds toward the same point in the sky. This isn't a loosely associated drift. It's a remarkably synchronized stream, as if every single car on every highway across an entire continent were subtly veering in the exact same direction at the exact same time. Finally, and most importantly, is the sheer inexplicability. The gravitational pull required to create a bulk flow like the one toward the great attractor, while immense, comes from a source within our observable universe. We might not see it clearly yet, but we know it's there. Dark flow defies this logic. The known and inferred matter in our cosmos, all the stars, galaxies, gas, and dark matter, simply cannot generate a gravitational gradient strong enough and coherent enough to orchestrate this motion over such distances. The gravitational influence of any structure diminishes with distance. For a source to pull on objects billions of light years away, it would need to be of such inconceivable mass that its effects would be overwhelmingly obvious everywhere in our nearby universe, warping the entire cosmic web. But our maps show no such monster. Therefore, the only conclusion is that the source of the pull must lie beyond our horizon, in a realm we cannot see, measure, or currently explain with our standard model of cosmology. This fundamental inexplicability, this pointing toward the truly unknown, is what sets dark flow apart and elevates it from a cosmic curiosity to a potential paradigm-shifting discovery. Magnetism is a force we experience every day, from the humble refrigerator magnet to the vast magnetic field that envelops our entire planet, shielding us from the sun's harmful radiation. It's a powerful, fundamental force of nature, and when we look out into the cosmos, we see its fingerprints everywhere, in the magnetic fields of stars, planets, and even threading through the vast expanses between galaxies. So when confronted with a mystery like dark flow, a natural question arises: could magnetism, rather than gravity alone, be the invisible hand guiding this cosmic current? This line of inquiry leads us into a fascinating, though highly speculative, realm of cosmology that considers the potential influence of magnetic fields on a truly universal scale. The idea isn't as far-fetched as it might initially seem. We know that magnetic fields exist on immense scales, weaving through galaxy clusters and even forming vast, faint filaments between them. These fields are thought to be primordial, meaning they were generated in the incredibly energetic chaos of the universe's first moments, potentially during the inflationary epoch or just after the Big Bang. If such fields were not perfectly uniform, if they had a preferred direction or a large-scale gradient, they could, in theory, exert a force on the ionized plasma that fills galaxy clusters. Since this hot gas is made up of charged particles, it can interact with magnetic fields. A sufficiently powerful and coherent magnetic field could potentially push or align this material, contributing to a coordinated flow. It's a compelling thought that the universe might be imprinted with a magnetic architecture from its birth, and that we are now seeing its subtle influence in the motion of the largest structures we can observe. However, turning this intriguing possibility into a viable explanation for dark flow runs into a series of monumental physical challenges. The primary issue is one of sheer strength. Magnetic fields weaken dramatically with distance, and the force they exert on charged particles is generally dwarfed by the overwhelming power of gravity, especially over the cosmic distances involved in dark flow. To orchestrate the motion of galaxy clusters billions of light-years apart, a magnetic field would need to be unimaginably strong and coherent across nearly the entire observable universe. The energy required to sustain such a field is staggering, far exceeding anything we see or can comfortably explain with our current physics. It would be like using a single, planet-sized magnet to make every compass on Earth point in the same direction simultaneously. The scale simply doesn't work. Furthermore, magnetic fields are directional. They have north and south poles. A large-scale magnetic field powerful enough to cause dark flow would create other, more obvious effects that we simply do not observe. It would polarize the light from distant quasars and the cosmic microwave background in a specific, detectable pattern. It would also influence the propagation of ultra-high-energy cosmic rays in ways that our observatories would have noticed. While we have detected faint, large-scale magnetic fields, their strength is orders of magnitude too weak to account for the high-velocity, coordinated motion of dark flow. They are more like gentle cosmic breezes, while dark flow requires a hurricane-force magnetic wind blowing from one specific direction for billions of years. Despite these formidable obstacles, the magnetic field hypothesis remains an active, if niche, area of research for a simple reason. It offers a potential explanation that resides entirely within our observable universe. Unlike the multiverse or superhorizon theories, a primordial magnetic field would be a phenomenon we could, in principle, study and measure directly through its effects on light and particles. Researchers continue to explore exotic models, such as fields generated by phase transitions in the early universe or amplified by the motion of cosmic strings, hypothetical, unimaginably dense defects in spacetime. These ideas push the boundaries of theoretical physics, but they serve a vital purpose. They force us to question our assumptions and explore every conceivable avenue within the known laws of nature before resorting to explanations from beyond our cosmic horizon. For now, magnetism remains a long shot, a tantalizing but faint possibility in the shadow of a much stronger gravitational pull. Yet it stands as a testament to the creativity and rigor of scientists determined to leave no stone unturned in solving this profound cosmic mystery. The search for a quantum theory of gravity represents the final frontier in our quest to unify the fundamental forces of nature, a puzzle that has stubbornly resisted solution for nearly a century. While phenomena like black holes and the Big Bang singularity are often cited as arenas where this unification must manifest, the vast, smooth expanse of the cosmos has generally been considered the domain of classical general relativity. Dark flow, however, violently disrupts this comfortable assumption, thrusting this large-scale mystery into the heart of quantum gravity research and suggesting that the quantum and the cosmic may be intimately intertwined in ways we never anticipated. At its core, the challenge of quantum gravity is the challenge of reconciling two beautifully successful but philosophically incompatible frameworks. General relativity describes gravity as the curvature of spacetime, a smooth, continuous geometry warped by mass and energy. Quantum mechanics, on the other hand, dictates that at the tiniest scales, the universe is grainy, probabilistic, and subject to wild fluctuations. Unifying them means figuring out what spacetime itself is made of at the most fundamental level. Dark flow enters this conversation by presenting a large-scale anomaly, a coherent motion across billions of light years, that general relativity, coupled with our known inventory of matter and dark matter, cannot explain. This failure opens a door, inviting physicists to ask if the solution might lie not in adding more stuff to the universe, but in modifying our understanding of gravity itself on cosmological scales. One prominent line of thought explores theories that are extensions of general relativity. These aren't outright replacements, but rather adjustments to Einstein's equations that introduce new terms or fields which only become significant over immense distances or in extremely weak gravitational fields. Theories like modified Newtonian dynamics, or MUND, though originally designed to explain galaxy rotation curves without dark matter, have been expanded into relativistic versions such as TVS tensor vector scalar gravity. Proponents of these ideas suggest that what we perceive as dark flow could be a manifestation of this modified gravitational dynamics. In this view, there is no mysterious pull from beyond the horizon. Instead, the laws of gravity themselves dictate a slight anisotropy, a preferred directionality on the largest scales that causes matter to stream in a specific way. The flow wouldn't be caused by an attractor, but would be an inherent property of how gravity works across the cosmos, a fundamental lopsidedness written into the laws of physics. A more radical and deeply fascinating possibility arises from holographic principles and emergent gravity theories. These ideas propose that gravity is not a fundamental force at all, but an emergent phenomenon, a side effect of the way information is encoded and processed on the boundary of the universe, much like the three-dimensional world of a video game emerges from the two-dimensional code on a disk. In such a model, the smooth, continuous spacetime of general relativity is an illusion that breaks down under certain conditions. Dark flow could be a signature of this breakdown, a glimpse of the quantum information theoretic plumbing beneath the cosmic facade. If the holographic principle is correct, the information describing our universe is stored on a distant boundary surface. A large-scale anisotropy or fluctuation in that underlying quantum information code could theoretically manifest as a bulk flow of matter within the observable universe. We wouldn't be feeling a pull from another universe, but rather reading a glitch in our own source code. This makes dark flow an exceptionally rare and valuable commodity in theoretical physics, a potential observational test. The mathematics of string theory, loop quantum gravity, and other candidate theories often produce a dazzling multitude of possible universes, many of which are impossible to distinguish through experiment. Dark flow offers a specific, quantifiable, and startlingly large-scale phenomenon that any successful theory must now account for. A theory that predicts a perfectly isotropic universe is now challenged by this data. A theory that naturally incorporates a multiverse might predict such flows as a common feature. By providing a clear, observational target, dark flow forces these abstract theories to make concrete predictions about the real world, potentially giving us a way to falsify some and lend support to others. It transforms the quest for quantum gravity from a purely mathematical exercise into empirical science, grounding our most esoteric speculations in the hard, puzzling data of observation. This concept of a universe that might be fundamentally lopsided leads us to a profound and deeply philosophical question. Could our very existence be linked to this mysterious current? To explore this, we turn to the anthropic principle, a framework that suggests the fundamental constants and conditions of our universe appear finely tuned to allow for the existence of observers like us. We typically apply this to the strength of gravity or the nuclear forces, but what if it also applies to the large-scale structure of the cosmos itself? What if the dark flow is not just a random anomaly, but a necessary feature of the particular cosmic neighborhood that allows our galaxy, our solar system, and us to exist? From this perspective, our position in the universe isn't just a random point on a map. It might be a special location where the conditions are just right. Imagine a vast cosmic ecosystem where different regions have vastly different properties. Perhaps in some areas, the gravitational tides from beyond the horizon are so violent that they rip nascent galaxies apart before stars can even form. In others, the expansion might be too rapid, preventing matter from clumping together into planets. Our observable universe, with its specific mix of dark energy, dark matter, and now this mysterious flow, could represent a rare Goldilocks zone on a truly cosmic scale. The presence of dark flow and our specific location relative to its source might be one of the many delicate factors that had to align perfectly for complex life to eventually emerge. It forces us to ask whether we live in a universe that is not only habitable but also oriented in a very specific way that is conducive to life as we know it. This doesn't mean the flow was created for us. That would be a misunderstanding of the principle. Instead, it suggests that in a potentially infinite multiverse containing every possible configuration of physical laws and initial conditions, we inevitably find ourselves in one of the rare universes, or a rare pocket of a universe where all the conditions, including large-scale flows, are compatible with our existence. We cannot observe a universe where dark flow is so extreme it sterilizes galactic formation, because in such a universe there would be no one to observe it. Therefore, the very fact that we are here to measure and debate dark flow means that its properties, however strange they may seem, must fall within a range that does not prevent the formation of observers. Its mystery is part of the package deal of our cosmic address, a feature of our local environment that we are only now becoming advanced enough to detect and question. History offers us a profound sense of perspective when confronting a mystery as deep as dark flow, reminding us that our current confusion is not an endpoint but a vital part of the scientific process. Time and again, an anomaly that defied all available explanations eventually became the key that unlocked a new and deeper understanding of the cosmos. Perhaps the most famous example is the perplexing behavior of the planet Mercury in the 19th century. For decades, astronomers were baffled by a small hiccup in its orbit, a slight drift of its closest point to the Sun, known as its perihelion, that could not be accounted for by Newton's laws of gravity, even after meticulously calculating the gravitational pull of every other known planet. Some proposed a hidden, unseen world within Mercury's orbit, dubbed Vulcan, to explain the tug, But the real answer was far more revolutionary. It wasn't a missing planet, it was a flaw in our fundamental understanding of gravity itself. The anomalous precession of Mercury's orbit became one of the first crucial pieces of evidence supporting Einstein's theory of general relativity, which described gravity not as a force, but as the curvature of spacetime by mass and energy. The puzzle wasn't solved by adding more to the existing model. It was solved by completely rewriting the model. We can see a similar pattern with the very discovery of the expanding universe. In the early 20th century, the prevailing scientific belief was in a static, eternal cosmos. The universe had always existed, unchanging and infinite. This view was so entrenched that when Albert Einstein developed his equations for general relativity, he famously introduced a cosmological constant, a fudge factor, to force his model to describe a static universe because that's what everyone thought was true. Then, observations by astronomers like Vesto Slipher and Edwin Hubble began to reveal a shocking truth. The spectral lines of distant galaxies were shifted toward the red end of the light spectrum, indicating they were all moving away from us. The universe wasn't static, it was expanding. The cosmological constant, which Einstein later called his greatest blunder, was hastily abandoned. The anomaly of the redshifted galaxies didn't just add a new fact, it completely overturned our conception of the cosmos, leading directly to the Big Bang theory. The puzzle forced a paradigm shift. Dark flow stands as the modern heir to these great historical mysteries. Like the orbital anomaly of Mercury, it presents a motion that cannot be explained by our current inventory of known forces and matter. And like the discovery of the redshift, it challenges a foundational principle of our cosmology, in this case the assumption of isotropy. The scientific response is also following a familiar path. Initial skepticism and a search for conventional explanations, like errors in measurement or unknown local structures, are a healthy and necessary part of the process. The proposed greater attractor is a direct parallel to the search for the planet Vulcan. It is an attempt to solve the puzzle within the existing framework. But if those searches continue to come up empty, we may be forced to consider a more radical conclusion, just as Einstein was over a century ago. Perhaps dark flow is not pointing to a hidden object within our universe, but to a fundamental incompleteness in our theories of gravity, cosmology, or the very structure of reality on the largest scales. It may be the subtle clue that guides us toward the next great revolution in physics, one that finally reconciles the cosmic and the quantum, or reveals our place in a far vaster multiverse. These historical precedents teach us to embrace such profound puzzles, for they are not obstacles to understanding, but rather the very signposts pointing toward a deeper truth. When a scientific discovery carries a name as evocative as dark flow, it's almost guaranteed to ignite the public imagination in a way that more technical terms simply cannot. This phenomenon didn't just make headlines in academic journals, it spilled over into mainstream news, documentaries, and countless online forums, often presented with a thrilling sense of cosmic mystery. Media outlets, always in search of a compelling narrative, frequently framed dark flow with phrases like mysterious force, universe being pulled, or evidence of another universe, tapping into a deep, almost primal curiosity about what lies beyond the known edges of our existence. This kind of coverage is a double-edged sword. On one hand, it generates widespread excitement and enthusiasm for astronomy, drawing public attention to the profound questions that cosmologists are grappling with. It transforms complex data into a story, making the universe feel dynamic and strangely personal, as if we are all passengers on a spaceship being drawn toward an unknown destination. This narrative captures a sense of adventure and wonder, reminding people that science is not a static set of facts but a living, breathing process of exploration at the very frontier of knowledge. However, this exciting narrative also carries a significant risk of misunderstanding. The line between a tantalizing, unconfirmed hypothesis and a proven fact, can become dangerously blurred in the rush to tell a captivating story. The intricate statistical debate, the ongoing skepticism from parts of the scientific community, and the very real possibility that the signal could be a systematic error, these crucial nuances are often the first elements to be lost in translation for a general audience. When a documentary dramatically asks, "Is another universe pulling on our own?" without equally emphasizing the vigorous scientific debate surrounding the data, it can create a perception that the multiverse is a foregone conclusion rather than one highly speculative interpretation among several. This places a tremendous responsibility on scientists and science communicators to navigate a delicate balance. How to share the thrilling potential of a discovery without oversimplifying the complex and uncertain reality of the research process. It's about fostering a sense of informed wonder rather than uncertainty speculation. This public fascination with dark flow reveals something fundamental about our relationship with the cosmos. Humanity has always looked to the sky for stories, from ancient myths about constellations to modern science fiction about distant galaxies. Dark flow fits perfectly into this grand tradition. It provides a scientific framework for a story we seem instinctively drawn to. The idea that we are not alone, that our universe is part of something infinitely larger and more mysterious. It's a concept that resonates on a philosophical level, challenging our place in the grand scheme of things and suggesting that reality might be far stranger and more wonderful than our everyday experience allows us to perceive. In this way, dark flow does more than just advance a scientific debate. It becomes a cultural touchstone, a gateway for the public to engage with profound cosmological questions about the nature of existence, what lies beyond the horizon, and our own tiny yet curious role in an ever-expanding, mysterious universe. Beyond its profound implications for cosmology, dark flow serves a remarkably practical and inspiring purpose right here on Earth. It is a masterclass in the scientific method unfolding in real time. For educators and students alike, this ongoing mystery offers a perfect, dynamic case study that vividly illustrates how science truly works, far from the stale image of a fixed set of facts in a textbook. It demonstrates the entire life cycle of scientific inquiry, from the initial shock of an unexpected anomaly to the fierce, collaborative debate that drives understanding forward. A student learning about science isn't just memorizing the laws of physics. They are seeing those laws being stress-tested, questioned, and potentially rewritten. Dark flow shows that the frontier of knowledge isn't a distant line on a map. It's a vibrant, sometimes chaotic, and always fascinating workshop where discovery happens. Consider the first lesson it teaches, the role of anomaly and curiosity. Science doesn't advance by simply confirming what we already know. It leaps forward when something doesn't fit. The moment Alexander Kashlinsky's team noticed that the data from hundreds of galaxy clusters weren't behaving as the standard model predicted was a classic scientific spark. It's a moment every student can relate to, the experience of a failed experiment, an unexpected result, a calculation that doesn't add up. In the classroom, this is often seen as a setback. But dark flow reframes it as the most exciting possible outcome. That initial perplexity is not an end point, it's the starting gun for a much deeper investigation. It teaches the value of paying attention to the tiny inconsistencies, the slight whispers in the data that hint at a much larger story waiting to be uncovered. The subsequent debate within the cosmology community is an equally valuable lesson. It showcases science not as a monolithic authority, but as a living, breathing, and wonderfully human process of skepticism and verification. When one team publishes a stunning claim, others don't simply accept it. They try to tear it apart. They search for hidden errors in the methodology, propose alternative explanations, and conduct their own independent analyses. This isn't a sign of dysfunction. It is the system working exactly as designed. for a student, seeing respected scientists passionately disagree over the interpretation of the same dataset is incredibly revealing. It dismantles the myth of the lone genius and replaces it with a more accurate picture of a diverse community, rigorously checking and balancing each other's work. The heated discussions over the Planck satellite data, for instance, are a powerful demonstration of how new evidence is constantly integrated, forcing theories to adapt and evolve. Ultimately, dark flow illustrates the gradual, iterative nature of building knowledge. A definitive answer may remain out of reach for years, but each paper published, each new analysis conducted, and each proposed theory, whether it invokes multiverses or magnetic fields, adds another piece to the puzzle. Even failed explanations are valuable. They eliminate dead ends and sharpen the questions we need to ask next. This teaches a crucial lesson about perseverance and intellectual humility. Students learn that major breakthroughs are rarely eureka moments, but are more often the result of decades of patient, collaborative effort, wrong turns included. The mystery of dark flow, still unresolved, empowers the next generation of scientists by showing them that the most important questions are still open, waiting for new minds equipped with new tools to finally solve them. It transforms them from passive learners into potential participants in one of the greatest detective stories the universe has ever offered. Perhaps the most profound impact of dark flow is not on the equations we write, but on the fundamental questions we are compelled to ask about the nature of reality itself. This isn't just a puzzle for astronomers, it is a deep philosophical provocation that forces us to reconsider the very limits of human knowledge and our place in the cosmos. For centuries, the foundation of science has been observation, the belief that we can see, measure, and ultimately understand the universe through careful study. But what happens when the most compelling evidence points squarely towards something that is, by its very definition, unobservable? Dark flow draws a stark line in the sand between the knowable and the unknowable, challenging the very premise that we can have a complete picture of reality from our limited vantage point. This forces a humbling confrontation with the concept of the cosmic horizon. We are used to thinking of the universe as everything that exists, but in a very real, physical sense, our universe is only what we can see, a finite bubble of space from which light has had time to reach us in the 13.8 billion years since the Big Bang. Everything beyond that horizon is causally disconnected from us. No information, no light, no influence can cross that boundary. Yet dark flow whispers that this is not entirely true. Gravity, it seems, might be the one thing that can hint at what lies beyond. We are like sailors on a fog-shrouded ocean, unable to see the distant shore but feeling the undeniable pull of its tide. This creates a bizarre paradox. We may be able to infer the existence of something we can never directly confirm, a truth forever just out of reach, making the universe feel both tantalizingly rich and frustratingly closed. This mystery also challenges our perception of reality's uniformity. The cosmological principle comforts us with the idea that the universe is essentially the same everywhere, a vast, homogeneous expanse where the same physical laws apply in every corner. It allows us to be cosmic cartographers, confident that mapping our local neighborhood gives us a reliable picture of the whole. Dark flow shatters that confidence. It suggests that our bubble might be a backwater, a provincial town in a metaverse of unimaginable diversity. What if the regions beyond our horizon are not more of the same? What if they contain geometries of space, concentrations of energy, or even different physical constants that would be utterly alien to us? The flow could be our first hint that we are not in a typical region, that our reality is just one flavor in a cosmos of infinite variety, forever redefining what we mean by the universe. Ultimately, dark flow holds up a mirror to our own existence, reflecting the audacious ambition and inherent limitations of the human mind. We are a species that evolved to navigate a world of medium-sized objects moving at medium speeds, and yet we have stretched our intellect to conceive of quantum foam and cosmic expansion. This phenomenon, however, might represent a frontier our brains are simply not wired to fully grasp. We can write equations that point to its possibility, but truly internalizing a reality where our entire observable universe is just a speck in a larger structure, being pulled by a force from a realm that operates outside our laws of physics, may be a cognitive leap too far. It is a stark reminder that the universe owes us no obligation to be comprehensible, and that the greatest mysteries are not just out among the stars, but are also buried deep within the limits of our own understanding. The quest to unravel dark flow has never been the work of a single nation or a solitary team of researchers. It is a shining example of how modern science operates on a global stage, a collective human effort to understand our place in the cosmos. This isn't a competition but a collaboration, drawing on the finest minds and most advanced technology from every corner of the world. NASA's Wilkinson Microwave Anisotropy Probe provided the initial stunning data, but confirming a signal this subtle required the powerful cross-check of the European Space Agency's Planck satellite with its even more sensitive instruments. This transatlantic partnership was crucial, as each agency brought its own unique expertise and technological prowess to the table, allowing for independent verification and a more robust analysis of the same mysterious signal. The data from these missions became a universal resource, a cosmic dataset pored over by research teams from Japan to Brazil, from India to South Africa, each applying their own sophisticated statistical models to the problem. This international endeavor extends far beyond space agencies. Universities and research institutions across the globe have dedicated countless hours and immense computing power to this single puzzle. A theoretical physicist in Germany might develop a new model for anisotropic inflation, while a data analyst at a university in Chile devises a novel algorithm to filter galactic dust from the Planck data with greater precision. An observational astronomer in Australia uses a ground-based radio telescope to study the peculiar velocities of clusters in the southern sky, adding another crucial piece to the puzzle. This decentralized worldwide network of expertise is the engine of modern discovery. No single country has a monopoly on curiosity or intellectual firepower, and by sharing data, challenging each other's methodologies, and publishing findings for open scrutiny, the global scientific community acts as a powerful system of checks and balances, ensuring that any eventual conclusion is as solid as humanity can possibly make it. This model of cooperation is not just beneficial, it is absolutely essential for tackling mysteries as profound as dark flow. The costs involved are astronomical, both in terms of funding and intellectual capital. No single nation could reasonably shoulder the entire burden of building, launching, and operating a mission like Planck alone. By pooling resources and coordinating efforts, we achieve far more than any of us could independently. But perhaps more importantly, we pool perspectives. A scientist raised in one culture might approach a problem from a slightly different angle than a colleague from another, and that diversity of thought is invaluable when confronting a problem that has defied conventional explanation. Solving a riddle that lies beyond the edge of the observable universe requires every tool at our disposal, not just technological tools, but the tools of human imagination, creativity, and collaborative spirit, all working in concert to peer into the unknown. But to truly embrace the radical fringe of dark flow explanations, we must venture into theories that sound more like science fiction than settled science, yet are seriously debated by some of the most brilliant minds in cosmology. The most extreme interpretation suggests that the source of the pull isn't just from beyond our observable universe, but from a time before time itself, from a reality that existed before the Big Bang. This idea completely inverts our standard narrative of cosmic genesis. Instead of a singular, definitive beginning from a point of infinite density, some models propose a cyclical universe or a bounce, where a previous cosmos contracted down to a super-dense state before rebounding into our own expanding universe. In this view, the immense structures of that prior universe, its own superclusters and gravitational landscape, could have left a ghostly imprint on the newborn fabric of our cosmos. Dark flow, then, wouldn't be a current within our universe, but the lingering gravitational memory of a world that came before ours, a cosmic tide still flowing from a long-vanished ocean. This line of thinking naturally dovetails into the mind-bending realm of extra dimensions, a cornerstone of string theory. Our everyday experience is confined to the 3 dimensions of space and 1 of time, but many physicists are convinced additional spatial dimensions are curled up or compactified at scales too tiny for us to perceive. The extreme hypothesis is that dark flow is evidence of these dimensions unraveling on a cosmic scale. Imagine our 3-dimensional universe is a membrane or a brain floating within a higher dimensional space. Another massive 3-dimensional brain, another entire universe, could be floating parallel to ours in this higher dimensional bulk. While we are forever separated and unable to see this neighboring universe, gravity, uniquely among the fundamental forces, could leak across the dimensional divide. The coordinated pull of dark flow in this radical model is the gravitational influence of that other universe, a parallel cosmos so close and yet so forever distant, gently tugging on every galaxy cluster in our own. Perhaps the most controversial idea of all is that our entire cosmological framework is built on a fundamental misperception. We assume our universe is the top-level structure, that there is nothing larger. But what if our universe, with its Big Bang, its dark energy and its galaxies, is merely a component of a far grander system? An analogy would be an individual cell in a vast organism, completely unaware of the body it helps to constitute. In this view, our universe might be one cell in a cosmic superstructure, a multiverse not of parallel realities but of interconnected cosmic domains, each with its own Big Bang, but all bound together within a meta-reality that operates under its own, as yet unknown gravitational dynamics. The pull we detect as dark flow would then be the internal gravitational mechanics of this larger structure, the vast circulatory system of a supracosmic entity on a scale so immense that our entire observable universe is just a single moving part within its whole. This isn't just a new force, it's a complete redefinition of what the universe actually is, suggesting we are living inside something much larger, whose true nature and rules we are only just beginning to faintly sense. Ultimately, the profound importance of dark flow research lies not in any single answer it might provide, but in the fundamental questions it forces us to ask. This is far more than an academic debate over a peculiar data point. It is a direct challenge to our entire cosmological framework, a potential key that could unlock doors to realms of physics we have only dreamed of. Solving this mystery wouldn't just add a new chapter to our textbooks, it could very well require us to tear up the old ones and start anew. Imagine the revolution if we confirmed that the gravitational source of the flow is indeed from beyond our observable horizon. This would be the first empirical evidence that our universe is not a self-contained island, but part of a much larger and likely more exotic structure. It would force us to finally develop a true theory of quantum gravity, one that can account for such vast, non-local influences, potentially unifying the forces of nature in a way that has eluded us for a century. We would have to abandon the comforting assumption of a uniform cosmos and embrace a lopsided, anisotropic reality, fundamentally rewriting our story of cosmic evolution from the Big Bang to the present day. The implications stretch from the origin to the ultimate fate of everything. If dark flow is a relic of the inflationary epoch, a primordial hill in space-time, then understanding its nature would give us an unprecedented window into the universe's first moments, a time currently shrouded in complete mystery. We could learn what triggered inflation, how it proceeded, and what conditions were imprinted on the fabric of reality before the first particles even formed. Conversely, if the flow is evidence of a multiverse, it would radically alter our perspective on our own place in existence. We would have to accept that our universe is just one bubble in a grand cosmic foam, each with potentially different physical laws. This wouldn't just be a philosophical shift. It would provide a concrete mechanism for explaining the apparent fine-tuning of our own universe's constants, suggesting that we simply reside in one of the rare bubbles where conditions are right for life. The flow would be our first tangible connection to this vaster multiversal ocean. Furthermore, unraveling this enigma could provide critical insights into the other great cosmic mysteries, particularly dark energy and dark matter. The gravitational dynamics required to explain a flow of this scale might reveal a deeper connection between these seemingly separate phenomena, perhaps showing that dark energy is not a constant but a dynamic field that varies across the cosmos, or that dark matter possesses properties we never anticipated. This knowledge wouldn't just satisfy our curiosity, it would allow us to predict the universe's ultimate fate with far greater accuracy. Will the expansion continue forever, leading to a cold, dark fade-out? Or could the mysterious force behind dark flow eventually overcome dark energy, leading to a cosmic reversal or a dramatic collision with another domain of reality? The answer to dark flow could tell us how the story of everything ends. Perhaps most profoundly, this pursuit matters because it exemplifies the very essence of scientific exploration, the courage to venture into the unknown and question deeply held beliefs. For centuries, we believed the Earth was the center of the universe. Then we believed the Sun was. Then we believed our galaxy was the entire cosmos. Each time we were humbled, and each time our understanding grew richer and more magnificent. Dark flow represents the next great humbling, a stark reminder that there is so much we still do not know. It is a beacon at the frontier, calling us to look beyond our cosmic horizon and question the very nature of reality itself. Whether the final answer lies in a new type of gravity, a ghost from a prior universe, or a pull from another cosmos entirely, the journey to find it will undoubtedly expand not just our knowledge, but the very boundaries of human imagination. As we reach the end of this cosmic journey, let's take a moment to reflect on the 30 astonishing facts we've explored about dark flow. We began with its shocking discovery in the data from the WMAP satellite, where astronomers found galaxy clusters streaming at over 2 million miles per hour toward a mysterious destination. We defined it not as a local current, but as a potential universal flow, a coordinated motion on a scale so vast it defies our standard model of cosmology. We grappled with its impossible speed, a velocity that outstrips even our sun's journey around the galaxy, and its defiance of the fundamental Hubble expansion, suggesting a pull from beyond our observable horizon. We traced its eerie direction toward the constellations of Centaurus and Vela, a path that points far past the known great attractor to something infinitely more profound. This discovery directly challenged the bedrock cosmological principle, the long-held assumption that the universe is uniform in all directions, forcing us to consider that our cosmic neighborhood might be fundamentally lopsided. We distinguished it from other bulk flows, emphasizing that this is not a regional anomaly but a motion encompassing billions of light years, a true universal current that cannot be explained by any known gravitational source within our cosmos. We saw how even the immense influence of dark matter falls short of providing an answer, as its distribution should cancel out over such distances, leaving us to look for a source beyond. We unpacked the ingenious detection method using the kinematic Sunyaev-Zeldovich effect, where the ancient light of the cosmic microwave background serves as a stationary backdrop to measure the motion of colossal galaxy clusters. We delved into the intense scientific debate surrounding its statistical significance, a rigorous process of claim and counterclaim that exemplifies science at its best, and we examined how the more precise data from the Planck satellite confirmed a large-scale anomalous motion, refining but not dismissing the mystery. We attempted to visualize the staggering distances involved, a flow across billions of light years that represents one of the largest coherent structures ever detected. We connected it to cosmic inflation, pondering if it could be a relic from the universe's violent birth, a primordial wrinkle in space-time frozen into existence during that first explosive moment. We then ventured into the truly extraordinary, considering if dark flow could be the gravitational pull of another universe in a vast multiverse, a concept that pushes the very boundaries of scientific inquiry. We also explored more conventional alternatives, from subtle data processing errors to the possibility of an unseen, hypermassive structure within our own cosmos. We compared it to the historical mystery of the Great Attractor, highlighting how dark flow is a different beast entirely, requiring a source of unimaginable power from a realm we cannot see. We examined its complex relationship with dark energy, the opposing force driving the universe's acceleration, and found that while they may dance together, they remain distinct enigmas. We investigated its potential role in the Hubble tension, the puzzling discrepancy in the universe's expansion rate, and considered how this cosmic current might be subtly skewing our measurements. We look to the future, to powerful new tools like the Roman Space Telescope and the use of fast radio bursts, which promise to bring sharper clarity to this profound puzzle. We dissected the fierce battle over statistics and the ever-present risk of systematic errors, a reminder of how difficult it is to measure the faintest whispers of the cosmos. We placed it in context against other cosmic motions, solidifying its status as the largest and most inexplicable flow ever detected. We even entertained the radical fringe, from the influence of colossal magnetic fields to ideas emerging from quantum gravity and holographic principles, showing how this mystery forces us to question the very fabric of reality. We applied the anthropic principle, wondering if our existence itself might be tied to this current, and we drew inspiration from history, seeing how anomalies like Mercury's orbit once paved the way for Einstein's revolution. We considered its impact on culture and public imagination, and its incredible value as a teaching tool that showcases the dynamic human process of science. Finally, we confronted the deepest philosophical questions it raises about the limits of knowledge and the true nature of reality beyond our horizon. This phenomenon represents the absolute cutting edge of cosmological research, a mystery that humbles us and excites us in equal measure. It reminds us that science is not a static set of answers, but a living, breathing process of questioning, debate, and discovery. The story of dark flow is still being written, and it invites all of us to be a part of it. So we'd love to hear from you. Which aspect of this cosmic mystery do you find most intriguing? Is it the possibility of a multiverse, the challenge to our fundamental principles, or the sheer scale of it all? Share your thoughts in the comments below, and let's continue this adventure of discovery together. Now that we've journeyed to the edge of the known universe and back, I want to leave you with a little cosmic homework, a way to take this sense of wonder from the screen and out into the night. The next time you find yourself under a clear, dark sky, away from the city lights, I challenge you to simply look up. Find that patch of space between the constellations of Centaurus and Vela. You won't see the dark flow, of course, but you can contemplate the profound mystery it represents. Consider that everything you can see, every star, every faint smudge of a distant galaxy, is not just drifting apart in the expanding universe, but is also part of an immense, invisible river flowing with purpose toward an unseen destination. That act of contemplation, of connecting a mind-bending scientific concept to the tangible beauty above you, is where the true magic of astronomy lies. If this has ignited a deeper curiosity to understand the mechanics behind the mystery, there are incredible resources waiting for you. For a deep dive into the original research, I recommend looking up the papers by Alexander Kashlinsky and his team. They're complex, but even reading the abstracts can be fascinating. For more accessible learning, websites like NASA's A Universe Discovery Guide and the European Space Agency's dedicated Planck mission pages offer articles, visuals, and interactive features that break down these complex ideas. YouTube channels like PBS Spacetime and Dr. Becky offer fantastic deep dives into cosmological phenomena with clarity and enthusiasm. And for those who love a detailed narrative, books like Brian Greene's The Hidden Reality explore the concepts of multiverses and cosmic horizons that make dark flow such a thrilling puzzle. Your engagement is what fuels this entire journey of discovery. If you've enjoyed pondering this profound mystery with me, please consider subscribing to the channel and hitting the bell icon. We are constantly exploring the furthest reaches of science, from the enigmatic nature of black holes to the puzzling world of quantum mechanics, and we'd love for you to join our community of curious minds. Let us know in the comments which theory you find most compelling. Is it the pull of another universe, a flaw in our understanding of gravity, or something else entirely? Your thoughts and questions inspire future content. Thank you for venturing this far into the cosmos with me. Keep looking up, stay curious, and never stop wondering about the incredible universe we call